general than this series, which is focused on instruments themselves. Now, physics, as students tell me, is a hard subject. One of the reasons I decided to study it at university was because the hardest subject I could find that I could actually do. There were other subjects like mathematics, which I found too difficult, so I skipped those. But it is a difficult subject and frightens people at some time, which is a pity, because one of the things it does, besides just give you information, is it helps train thinking. It's a problem-solving discipline, and I always tell students that no matter what they decide to study, the thing that is useful in terms of employment is your ability to solve problems, and physics is very good at that. So the hardest physical concept I've tried to get across to you has been impedance. And so I'm going to try again, which I sort of apologize for, but not really. That's kind of my job. Imagine you are the water engineer for Cape Town, and it's your job to design the water delivery system. So you know how many people live in the area, you know how much a given household takes for water, and so you know how big to make the pipe. However, you also want to plan for the future. You want to think 20 years in advance and say the projections are that 20 years in advance there will be twice the population, let's imagine. And so you need to design a pipe which is big enough. Now, when you decide on a pipe, the ability to push water through, which depends on the resistance or impedance of the pipe, depends on how big the pipe is, how long the pipe is, on the roughness of the walls of the pipe, that is the friction with which the water goes, but it is also depends on the speed of the water. So that if you have reservoirs that say 300 meters and 1,000 meters and 2,000 meters, the speed of the water will be different from those various things because of the height difference. So you have to take that into effect as well to design the pipe system. And that's the problem of calculating the size, the proper size of the pipe. Now, if the population doesn't double, you're in trouble because you've wasted money. If the population triples, you've made too small a pipe, etc. But you know, you have to make some planning. In terms of your television set, coming down the cable that brings in are different channels, many different channels, and they all have a different frequency. They all have a different height, if you will, of the reservoir, several hundred different frequencies. And therefore, what the input of the television looks like depends on what channel you're tuning. So just as with the water pipe, you have to design the input to the television so it is a guess of the best possible system. And that's kind of what I mean, I'm talking about in impedance. So that in the instruments we've talked about, the bell of the trumpet or the French horn or of the clarinet, etc., you've got different waves of different frequency and different wavelength coming down, and you want to get them out so that people can hear them. And in order to do that, you need to make the bell, you need to curve the bell so that the radius of curvature of the bell at some given point is equal to the wavelength of the sound that you want to get out. And that's why the bell curves in the way it does. Okay, so that's the best I can do on this for the moment. So let's now talk about the voice. And I'm going to talk about some terms, harmony, consonance, and dissonance. The word harmony, oh, this is a different one. Where is my, There's the pointer. The word harmony means the agreement of parts to form a pleasing whole. It comes from the Greek word, the Greek noun for agreement or concord, and that in turn comes from the Greek verb meaning to fit together. And that's what harmony does. In physics, we have harmonic motion, such as this pendulum here, in which I have a regularity of motion. What I am doing is I am using my force to lift this object. I'm doing what would be called work against gravity, and then gravity pulls it back in the same way that I'm storing energy into this, in the gravitational energy, and I'm letting it go, and it is being transferred into motional energy back and forth in a vibratory fashion. In a string, such as we've seen, when I pull the string aside, I'm adding elastic energy, and I can convert that into motional energy back and forth. And so we get vibration, we get harmonic motion, which is regular motion. And I mentioned on Wednesday with the piano that consonants, I can have a tonic chord in C, I can have the subdominant C, F, A, C, and I can have the dominant seventh C, F, G, B. And these chords can be used to transition or modulate from one key to another. Then I have another term, consonants, which is two vibrations which sound pleasing to us because the ratios of the frequencies are simple. Friction is doing its thing there and slowing that down. Friction, of course, is not only painful, but it's also very useful because without friction, we couldn't walk. One of the things I try to tell my grandchildren is, how can you walk? And they say, well, I just walk. I say, well, if I want to move something, I have to push it. If I want to move me, what pushes me? And then they look at me, and I pick them up, because I can still do that, and I say, now walk. And of course, you can't walk. So what's pushing you is the earth. Newton's third law. I can't resist, I'm sorry. Now, the most consonant interval is the fifth. After the octave, which is 2 to 1, we have a consonant interval of 3 to 2, which is called the fifth. And the fifth is the most consonant because those two notes have the most harmonics in common. And they are sort of, that's the natural ratio at which two untrained people would harmonize in singing a song. The opposite of consonants is, of course, dissonance, where you have unpleasant sounds, but they are used, and I'm going to use some. In 1913, I think it was, whoops, wrong thing, Stravinsky premiered the ballet The Rite of Spring, of course, as many people know. And in The Rite of Spring, he used dissonance a lot. And this was very unusual at the time. It was in Paris. Nijinsky did the choreography. And there was a riot, a literal riot, where people were hitting each other over the head with umbrellas and screaming. And poor Stravinsky had to escape through the dressing room window and disappear into Paris. But see if I can make this work. This is part of the sacrificial dance. And so people who had grown up on Mozart and Schubert must have had a very difficult time listening to this. Anyway, enough of that. Consonant sounds are one in which there's a periodic, regularly repeating pattern. And why do they sound pleasant? Well, psychologists do studies on this kind of thing. And for example, first of all, here's more graphs, sorry. Here is a fundamental frequency in green with a wavelength of 1 unit, okay? And it's a very regular sinusoidal pattern, just like the motion of the pendulum. But then I have the first harmonic, which is this, which has a wavelength of twice or of half the size. And when I add those two together, they're just an octave apart. It's this note and that note together. And what you hear is this funny red thing, which doesn't look simple, but is very regular. And as I mentioned in Fourier analysis, I can take this complicated but regular series, and I can make it a combination of ordinary, very nice waves. But psychologists who study this kind of thing do the following. They take untrained people, I mean people who don't listen to a lot of music, and they play pitch intervals, and they ask them, is this pleasant or not? And so if they play 2 tones that are identical, everybody says that's fine. And then as they move up a half tone or so, and they get, people say, oh, not pleasant at all. And then as you increase the interval, when you get up to about minor third, people start to claim that's already now a pleasant sound. Okay? We don't understand why, but it is a measurable and repetitive result. And it seems in some sense as if our brains are wired for music. On Monday, I worried about what the oldest instrument was, a horn or a drum, but surely the oldest instrument is the voice. And I can imagine back in the days when we had various ancestors living in Sterkfontein in the cave, that mothers would comfort their babies by singing to them. And even baby talk, you know, oh, you sweet little thing, that kind of talk that we use to infants is melodic, and psychologists again have shown that this helps train infants to the sounds of their native language. So it's important to talk that kind of sweet babble to little kids. The composer Jean-Philippe Rameau was the first person to talk about the theories of harmony, and he published a treatise on harmony in 1722, and that was the first major work we have in existence on music theory. He died in 1764, and the story is told that on his deathbed he was complaining to the priest that he was chanting out of tune. That's a serious musician, all right. Now, the human voice is an incredibly sublime instrument, and I understand there are people who don't really yet appreciate the sublimity of the voice, but eventually they will. No other instrument we have can express so many shades of meaning, of emotion, can thrill or frighten, can delight or menace, etc. And the great opera and lieder composers have taken advantage of this to create music. We know that the Greeks used music in their dramas, but we don't know what it was. What they actually did. In the very oldest times of the church, the congregation would sing, but as I mentioned, I think yesterday, in 367 of the Common Era, the Council of Laodicea banned congregational singing and said it had to only be left to the priests and those who had been trained. And then by about 600 of the Common Era, Pope Gregory, called Gregory the Great, set up schools to teach singing, to teach church singing for priests and monks, and his name is associated with this in the terms of Gregorian chant. And Gregorian chant is based on simple ratios, 2-to-1, 3-to-2, and 4-to-3. So that's the octave, the fifth, and the fourth, and that's it. But about after about 1,000 years, sort of in the higher Middle Ages, when singing and music became popularized, and we had troubadours and meister singers, and there was music outside the church, other intervals and abilities to make melody changed, and people started to adopt a system which had been proposed already back around 150 by Ptolemy, the same man who created the idea of the Earth-centered universe. If we've got 2 and 3 and 4, why not 5? And so he invented the third. The church would not use the third in Gregorian chant, but it was used. And at the same time, as I've mentioned before, polyphony began, which is use of 2 melodies at the same time. And in the great cathedrals that you can see built in the High Middle Ages, there are often 2 organs in opposite sides of the nave. The most ornate and famous ones I've seen have been in St. Mark's Church in Venice, which are really very lovely things. Venice, of course, was a very rebellious area for the papacy, so they sort of put up fingers to whatever the Vatican had said. But during the Avignon papacy in 1324, John the 22nd was the Pope, and he was very unhappy with the modern trend, and he made the following statement: only concords such as the octave, the fifth, and the fourth that enriched melody may be sung above the ecclesiastical chant. And he declared thirds to be immoral, and so they were not used. The great polyphonic writing for the voice used 4 basic voices: bass, tenor, alto, and discant, or a lead singer, and the other 3 voices would sort of improvise around that. And then later the madrigal became popular, and with the higher voice parts being taken by young boys. Training young boys was a long business, and then of course they'd reach puberty and the voices would change and break in adolescence. And this led to the rather horrible business of the castrati singer, which I will ignore for obvious reasons. But wonder of wonders, it also led to the discovery that women could sing, amazingly. And so the soprano came into existence, not in the church, of course, but in other music. So in the church, castrati voices were still used, and there was very florid and virtuosic singing, the highlights of that rather dubious profession. And of course, the sooner we got to sopranos, the better. And sopranos were able to sing ever higher, so that, for example, the tenor voice goes from C3 to C4, which is a fairly high C, and then the highest C, which is C5. But the soprano voice it goes from C4, C5 to C6, which is the high C. However, Mozart, in The Queen of the Night, has an F6, which is extraordinarily high. Except in Mozart's time, the pitches were not quite the same, so it was really an E6. But still, blasted high, I would say. The growth of opera in the 18th and 19th century meant that it was necessary to get the voice out over a large orchestra, particularly a loud orchestra with brass instruments. And so projection became an important part in the voice. And this change, of course, is particularly crucial in Wagnerian opera, where the tenor and soprano voice really needed to use what's called chest voice to project out. And so the joke goes that the 19th century style of singing for Bellini and Donizetti, called bel canto, for beautiful singing, was replaced by can belto, for getting the voice out over the orchestra. What has changed, not for opera but for popular music, is the use of the microphone. Crooning, typified by Bing Crosby, for those of us who might actually remember him, became popular, and also blues with wonderful singers like Bessie Smith and Louis Armstrong, also very popular, and also using electronic amplification. And a real change, of course, came with first rhythm and blues and then rock and roll, and the preference for untrained voices as opposed to trained ones. And there's no soprano, alto, tenor, bass in rock music. Now, the voice is produced by what are called the vocal folds, we call them the vocal cords, but they're not cords, they're folds of flesh. And they sit just above the trachea. I have both a picture and there's a model which has kindly been lent to us. But here what we see are the vocal folds, and they sit here just above the separation between the trachea, which leads to the lungs, and the esophagus, which leads to the stomach. And there is this piece here, the epiglottis, which is supposed to prevent, when we swallow, things from going down the trachea into the lungs and allowing them to go into the esophagus and then eventually to our stomach. So, as always for music, we need a generator, a resonator, and a radiator. We need something to generate the vibrations, something to amplify them, the resonator, and something to get them out, namely the radiator. And the production, the generator is, of course, these vocal folds, which exist here. Here we have the larynx, which we would call the voice box. And then up here comes the pharynx, this longer tube. The pharynx then leads to the mouth, which is called the oral cavity. And the shape of this oral cavity is determined by the tongue and the palate, the hard palate here, which is the roof of the mouth, and in the back where the tongue is the soft palate. And then there's another area of valve over here leading to the nasal cavity. Now, the next two slides show us pictures of a diagram of the vocal folds. Here you can see closed and open. And then, for those of us who are not too concerned, there is the real thing. And looking down into the trachea here, you can see the rings inside the trachea. Somebody putting a laryngoscope down with a camera to take a picture of someone's, and you can see the cartilage that can control the folds, etc. That's this piece over here. Now, here again, we have a situation which is a vibratory situation in which I've got something to pull something apart, add some tension to a string, if you will, and then a restoring force, the elasticity, to pull it back. But this is not similar to what happens in a wind or brass instrument. It's much more complicated. I can't resist. Every day I have to show you Mersenne's formula, every day. because formulas matter, okay? So what we are doing with the vocal folds is we're increasing the tension. We put tension in them, and that, of course, increases the frequency. But the other thing we're doing is making them longer, and that's in the denominator, and that decreases the frequency. So there's a conflict there between what goes on. Now, in a wind instrument, the vibrations are caused either by a reed or by the player's lips. And the tube, the radiator, can only support frequencies of certain values, which depend on the length. And this doesn't work for the human voice. For example, a basso profundo, the really low, not those octavists that I played the other day, but they're amazing. But here's middle C, which is C4, and a good solid bass can get down to C2, which is 2 octaves below, or 4 times the wavelength. Okay? Now, that frequency of C2 is 65 hertz. Okay? And if I take, and remember, if I take the speed of sound, which is 340 meters per second, and I divide by 65 hertz, I get a wavelength of 5.2 meters. Okay. The vocal tract works like a tube that's open here but closed at the other end, and therefore the fundamental frequency is 1/4 of a wavelength. Do I have a picture of that? No, not yet. No, somewhere I have a picture of that. Okay, 1/4 of 5.2 meters is 1.3 meters, and so there would be a 1.3 meter frequency, fundamental frequency. Where is the tube from here to here that is 1.3 meters long? I'd have to be, that tall. So it's not doing what a brass or wind instrument is doing. It's really a very different and much more complicated system. A reasonable example would be, and I didn't bring one, but suppose I have a balloon and I blow it up and I'm holding the end and I let my fingers go and it squeaks a little bit. That's what the folds are doing, that kind of thing. Here is the frequency versus age for men and women, okay? Men, I mean, at very young ages, they're the same, and then they split at puberty. And men typically have voices a full octave lower than women, and that's a factor 2 in frequency. And when I said men have a high C of C5 and women of C6, that's what I was meaning. And you can see that it decreases with age, but then for men, it begins to increase. This is, my God, that's 100 years old or something like that. And trained voices can do somewhat higher frequencies as we return. Women's voices continue to deepen. Men's voices reach a bottom in their mid-40s and then start to increase a little bit. Now, at this point, this rapid change in the ability takes some training of the muscles. And that's why, as I mentioned, adolescent boys often have their voices change from here back up to here. So they get this falsetto break all of a sudden in their voice, which embarrasses the hell out of a 15-year-old, but not anymore, I don't care. Now, this is an attempt, it's a very complicated slide, but it's an attempt to show the vocal folds, what happens to the vocal folds as a function of frequency, where they're nice and relaxed here at low frequencies, and then they're tense as the frequency goes up, but then they change. again, as the frequency gets higher. That's probably too complicated to mess with very much, but it's real nonetheless. Oh my goodness, what is that? Well, the hell with that, let's skip that. That's not what I put on, I can assure you. What I had here was a picture of the normal voice where you see the fundamental frequency, and then this is a half a wavelength, and then the next was a wavelength and a half, and that's the fundamental for a falsetto frequency. You don't get as many harmonics, and that's why falsetto sounds thinner. Why, for example, a countertenor has a much thinner sound than a real honest-to-goodness Helden tenor, which I much prefer. Now, the frequency of speech varies from about 70 to 200 hertz for men, and twice that, 140 to 400 hertz for women. Singing is generally at a much higher frequency than that. And what I have here is the generator of the sound was the vocal folds here. But the resonator is the vocal tract leading from the pharynx up to the lips. And that has, like the body of a violin, which has different, the wood and the air in the violin, which has different resonant frequencies than the string, that has its own set of resonant frequencies. And what comes out are all these harmonics that are created by the vocal folds or chords and modified by this, and this is what comes out at the lips. Okay. Here's another picture. Depending on, this is 100 hertz. That's somewhere around here, about a B flat. And then 200 hertz, which would be an octave higher, but that's not important. So this is roughly how things get modified by the vocal tract. And here we have to talk a little bit about phonetics. Because for men, the vocal tract is about 17 centimeters in length, and for women, it's about 14 centimeters in length. So I'm going to take an average of in between those 15 and a half. Then for a vocal tract is a pipe closed at one end, and so at the mouth, at the lips, where the pressure is atmospheric, that's like a string tied out at the end, as you, I hope, recall. And then at the bottom, where molecules cannot move, the pressure is its maximum. And so that we get a quarter of a wavelength, we get 3/4 of a wavelength, we get 5/4 of a wavelength as the harmonics coming out of such a tube. For an average length of 15.5 centimeters, the frequency would be about 550 hertz for this. Okay? And the harmonics would be 3 times that, 5 times that, 7 times that, etc. The vocal tract, of course, is not a tube, but the numbers are close enough. Each vowel has its own unique set of frequencies to be, and these sets of frequencies are very important. They are called formants in phonetics, and they differ for different vowels, as we can see here. But I'm going to ask my singers if they would. Amateurs like me have, unfortunately, in order to be able to sing in choruses, have had to suffer through many, many singing lessons, which are intensely frustrating, I can tell you, if you don't have a great voice. But one of the things I can remember doing over and over is going, mi, va, mi, va, mi, va, mi, va, mi, back and forth to do vowel sounds. It's awful. But we have real professionals, and if I could ask them to articulate the vowels so that you could hear both from the soprano voice and maybe from the baritone voice as well, so you could hear the differences and watch the mouth. Louise, you could stand up so people can see you. Yeah, just, here, you want a note somewhere?
Yes, no. If you want to.
Pick a note. Okay, go ahead.
So would that mean?
Just do vowel sounds. A, E, I, O, U. And notice what happens to the mouth to do that. Could you go up a scale with a given vowel so I can hear what I want is there's a transition in the voice from what is called chest voice to head voice, and it's hard. And singing near the transition, which for the tenor occurs roughly at F sharp, is a painful area. But could you just do a scale so? Thank you. That's brilliant. Now, that's terrific. Oh, and could I ask you to do the same sort of thing? I'd like you also to watch the mouth, because one of the things that singers do is as they go up in the note is the mouth opens, and that has a physical thing very similar to the hand that goes inside the French horn. Please. Okay. What would you like? Picking the, pardon?
A D.
A D.
Yes.
I am so envious. Could you do a scale so I can hear the change? What's a reasonable low note for you?
Not really.
E?
Not really sure. Maybe we can try an E.
Well, no, I don't want you to do that. What I'm concerned about is composers write some really low and some really high notes. Okay. In the prologue to Pagliacci, the baritone comes out before. Many of you will know this, of course, and the end of that has an A flat, which is one hell of a high note for a baritone. But you don't have to. Can you do that? You want to do it? But can you go up through? Where's the transition in the baritone voice?
It's in the middle range. Like I can do the sipuo.
Yeah, can you?
It's
somewhere around there. Yeah. Can you do a scale going through that so we can hear the difference?
I'll just do the
Sure, anything.
Andiamo incominciate.
Ah, brilliant, brilliant. Thank you. Wow. And that is from Pagliacci. Andiamo, let's go. Incominciate, we get started, you know. Thank you. Oh, that's, wow. Wow, wow. Where am I? Here you can see a diagram of how the vocal tract changes with the phonetics of an A and an E and an U. And there's the tongue position, which changes significantly in that case. The lips, as I said, also matter because remember with the French horn, when Carolyn was here on Monday, and she put her hand inside the bell and took it out, and the frequency changed. So that what you're doing when you put your hand in the bell is you're moving the node back in, and that shortens the wavelength a little bit, and that increases the frequency and gives you a slightly higher note. Now, if you watch an opera singer, when they get to a high note, their mouths are wide open. And the reason for that is because that allows remember, there's air pressure, zero air pressure, there's atmospheric here at the lips. If you open your mouth wide, that